increasing, and at the same time strain is also increasing. And we see that after some point of time there is a change, and we see that now what is happening, the strain rate is faster. Okay, we'll come to that, but before that let's just check this region. Okay, what's happening in this region? In this region, what is happening, there is a linear increment of stress corresponding to strain, or vice versa. So in this region, what is happening, stress is, you know, okay, the strain is proportional to stress. It is increasing with a linear relationship. The stress is increasing by some amount, and at a constant rate, the strain is also increasing. So this is the linear increment that we are talking about in Hooke's law. So within elastic limit, again, what will be elastic limit? In this stress strain curve, the A point is a elastic limit. So by definition, what it means, that up to this point, okay, up to this point, if we apply our stress, there will be some deformation for sure, like the beam is elongated by some amount, say for example, okay, which is going to be very small. I'm drawing it with some exaggeration. So at this point, say somewhere here, okay, this is the amount of stress and this is the amount of strain. Stress is here and strain is here. At this point, if we remove the force, then the material will go back to its original size, original dimension. So that is elastic behavior. At that point, whatever is the deformation is elastic deformation. What is the condition? If we remove the load, the force, the material will go back to its original position. Okay, so up to a point that is going to occur. So a point is our elastic limit. Fine. Beyond a point, if we apply some load, okay, we are applying some load or force such that the stress is now greater than this a point. Now the stress is somewhere here, stress level. Now at that point, what will happen? There will be a permanent deformation. We have this steel bar. Now we have applied a force which has caused the stress to be more than the value at a point. Now if we remove the load or the stress, there will be some permanent deformation in the beam or the material that we are using. Fine. So in this Hooke's law, we are talking about this elastic region only. So Hooke's law is saying that within elastic limit, the stress is proportional to strain. Okay, or vice versa, strain is proportional to stress. Now this relationship, okay, this relationship is given by this E is the modulus of elasticity, or Young's modulus. This is given by stress divided by strain. Now this is the value for steel. We shall be using steel a lot, right? Reinforcements or other structural steel members, we will be talking about steel. So we have to know what is the modulus of elasticity of steel. 210 gigapascal. What is giga? 10 to the power 9. What is pascal? Newton per meter square. So this value we have to remember, we have to know. This is also given as 2 into 10 to the power 5 Newton per millimeter square. Okay, so this is the same value. We just have to know how we are changing the unit. Okay. Okay, you see this unit conversion once. If you don't understand, let me know. So this value and this value, they are the same value. We have to remember, just the units is different. We have to remember that value. Now, most of the time, this value will be approximately equal to 2 into 10 to the power 5 Newton per millimeter square for different types of steel. Similarly, there are different values for concrete. And then again, you know that concretes are of different grades, different strength, right? That way, concretes will also have some value. Aluminum will also have some value. So this is the property of the material, okay? This is almost constant for steel. It is almost constant for aluminum, but they are different values, fine? So that way, this modulus of elasticity or Young's modulus is a property of the material that we are using for the test. Now, okay, the Young's modulus is generally assumed to be same in tension or compression, and for most engineering application, it has high numerical value. Okay, it is a high numerical value for steel, for aluminum, etc. For concrete, it is very less in comparison to steel. Okay. Now coming to the stress strain diagram. Now this diagram is very important. We have to understand all the features. First is this A point. What is A point? A point is the elastic limit. That means up to A point, if we apply the load, there will be some elastic deformation. What is elastic deformation? If we remove the load or force, hence the stress, the deformation will vanish. Okay, it will come back to the original dimension, original size. So that is elastic limit. Then B point is the yield stress or upper yield stress. There are 2 points actually here, the B point and C point. B point is called upper yield point, C point is called lower yield point or lower yield stress point. Okay, that way. So what is happening in this B point and C point? This is a failure condition. Okay. So at this point, the material is losing its strength, its resistance. Now it is elongating at a much higher rate. Okay. Up to this B point, it was increasing slowly. Okay. It was deforming slowly at a uniform rate. You are applying force, you are increasing the load, and it is deforming slowly at a uniform rate. But from B point, what will happen? This elongation will increase. Now it is elongating very quickly, okay, with less amount of increase of stress. Fine. Say for example, there was 5 millimeter deformation for 50 kilonewton. Say for example, for 100 kilonewton, say for example, we are applying 100 kilonewton load. Say for example, there is 10 mm deformation. So what is happening? For every 50 kilonewton, 5 mm deformation is occurring. Say for example, now what's happening after yield point? Now the resistance of the material has decreased. Now for say for example, just for another 25 kilonewton load, we have, say for example, 10 mm extra deformation. Like that, for less increment of load or force, there will be larger increment in the deformation. So that is yielding. So in this region, there is yielding. So in this region, what is happening? This is a kind of a failure condition. The material is losing its strength. Okay. And we have two yield point. One is upper yield point and one is lower yield point. Okay. After this lower yield point, what is happening? Again, the material is slowly gaining some strength, but not like the previous case. Now the elongation is much faster. And this D point, this is the maximum load the material can take. This is the ultimate stress point. Okay, this is the maximum load the material can take. Fine. Hence the maximum stress. So there will be a corresponding strain. So this is the strain at maximum stress. And then after that point again, it is elongating very quickly. Now, say for example, it's going like this. Okay. At this point, what is happening? It is elongating very quickly, and a point will come, like here at E point, where there will be breaking of the member of the material, breaking or rupture will occur. So these are various important points in the stress strain curve. This is a stress strain curve of mild steel. Point A, this is elastic limit. Up to this point, the stress and strain are proportional. They are increasing uniformly. Okay. And also in this region, if we remove the load, the member will go back to its original position. Then B point and C point, they are the upper yield point and lower yield point. In this position, what is happening? The material is losing its strength. After this, if we apply load, there will be higher increment in the deformation. The deformation is at a higher rate. Fine. Then it goes up to D point. At D point, it attains the maximum stress. Hence, it is taking the maximum load. Fine. And after D point, it will again elongate very quickly. Now the load taking capacity is reducing. What is this curve is indicating? It is going down, right? It is going down, hence the stress is going down. It is the capacity of the material. The capacity of the material to take stress, that is to take load, is reducing after D point very rapidly. And at E point, we have nothing more after E point. That means E point is the failure point. At E point, the material fails, it breaks, it ruptures, and it is not able to take any more load. Okay. So this is another description of the same stress strain curve. Okay. So most of the time this elastic region coincides with the proportional limit, but sometimes it may not, but it will be very near. So that is what it is being shown. Up to A point, this is proportional. So here we are following Hooke's law. So by Hooke's law, what we get, that modulus of elasticity is equal to stress by, I'm sorry, I'm just using the mouse. Stress by strain, right? So the modulus of elasticity, say for example, steel is a constant, right? So if we know the strain, by multiplying with the modulus of elasticity, we can find out the stress level, or vice versa. If we know the stress, we can find out the strain, like that. This is for some analysis kind of thing. We can use this curve because the modulus of elasticity is a constant for the material. So for steel, we can plan, okay, this steel can take this amount of stress. For this amount of stress, there will be this amount of strain, right? Any material we are designing, say for example, we are saying that this is going to be the stress level. So from this graph, we can find out, okay, for this stress, this will be our strain, okay? So say for example, 0.01 is the strain, right? Then that is what, delta L by L. Now corresponding to the length of the member, you can find out, okay, this will be the total elongation or total deflection in the member. And using that value, you can use it for design. Say for example, you are designing some member in a structure. So what is the maximum deflection or maximum elongation allowed in the member, right? We are designing a member, we'll say that the maximum elongation that can occur, that we can allow, is 1 millimeter or 2 millimeter. That kind of calculations will start with this stress strain curve. Fine. Okay. Now, again, this is proportional limit, this is elastic limit, or the yield point, upper yield point, and we have a lower yield point. Here is a maximum, okay? And then we have this E point where fracture occurs. And this is called elastic region. Why? Because within this region, if we remove the load, the element will go back to its original position, and in this region it will not go back to its original position. There will be some permanent deformation that we call plastic chains. That is why we are calling this region plastic region, because there will be some permanent deformation if we increase the load beyond this point. Okay. So these are the definitions of various points: proportional limit, elastic limit, yield point, ultimate stress point, fracture or breaking point. We have already discussed this. You can go through the definition. Okay. So Hooke's law states that the strain of the material is proportional to applied stress within the elastic limit of that material. And we will use the Hooke's law to find out various conditions of stress and strain, which we'll be using in analysis and design, etc. Okay. So that will be all for here. Then we will go to discuss various type of elastic constant. Now, someone from your group need to tell me what you have learned about shear force diagram and bending moment diagram. Or if you have anything, any question regarding this stress strain curve, you can tell me now. You can ask me. We can discuss. Okay, I would like to mention one more point. Say we are designing a material, right? Say we are designing a building. Say for example, now we need to know the strength of the material that we are using, right? We are using steel. What is the strength we will be considering? We will be considering the strength corresponding to this lower yield point. Okay, corresponding to lower yield point, this is the stress level, right? So we will say that the yield stress of the material is 250. Say for example, I'm saying 250 Newton per millimeter square, right? So this is the yield stress. By using this value, we will be able to find out what is the amount of material that we require. We will have a requirement, right? We are designing a building. Say we have a requirement that it has to support 500 Newton force. That we have to handle, we have to resist 500 Newton. Okay, so what do you see that it can take maximum 250 Newton per millimeter square. So minimum we will require how much? 2 millimeters square. 1 millimeter square can take 250 Newton. We are handling 500 Newton, so minimum we will require 2 millimeters square. That way we will find out, okay, this is the amount of material we will require to resist the external load to design the building, to design the systems. Okay, then there will be some factor of safety. Now the factor of safety we will use so that there is a safety even when the loads are increasing, because whenever we are designing, we will not be able to say precisely that this building, this structure will be subjected to 500 Newton loads only. Okay, we will not be able to say that precisely. So therefore, there will be some factor of safety. We will be learning that in the design part. Maybe you are doing in structural engineering. There you will learn the concept of factor of safety and load combination based on what we will decide what load to tackle. Here we are saying if we know the load, if we know the force, right? What is the amount of material we have to put? Fine.